Hello, this is Mr. Craig. Alright, so the reason why I wanted to go over this is because there's a lot of material that I actually bring up as dialogue and actually just some random questions. I know that in the video I did discuss Nernst Equation, and why am I not seeing myself anymore? Oh well. Alright, so I am there. Alright, so let's take a look at a couple of these questions. And these questions were asked at the other school, and they were pretty good questions. So, first of all, what exactly is an electrode? What's an electrode? What is an electrode? And again, we spoke about what? Galvanic cells, right? So when we talk about a galvanic cell, how many chambers are there? 2. Good. Thank God you guys were scaring me there. So there's 2 chambers, and we have a solid. Oh, great, my pens aren't working. So we've got a solid in one of the chambers and another solid in another chamber. And how are those connected? By a wire. Good. So when we talk about an electrode is something that may be sacrificed for this process. And when we talk about an anode versus an anode, actually let's start with the anode. What happens to the anode, or what goes on at the anode? It's oxidized. So it's the site of oxidation. And if it's oxidized, then that means that if it's being oxidized, it's losing electrons, correct? Yeah. So if we say that this one is the anode, then the electrons are moving in this direction. They're going from the anode to the cathode. So this is our cathode. And so if the cathode is the site of reduction, then that means that it's gaining electrons, correct? So a typical AP exam type question, or a good NIMSY question, might discuss mass. So if we say this is the anode and this is the cathode, what could we say about the mass of the cathode? Is it going to get higher, lower, or remain the same?
High.
Why?
Because it's gaining electrons and that's going to create a solid around the solid they're in.
Very good. So what that means is we have ions that are in the solution here, and as the electrons come onto the site, it actually allows that ion to bind and actually start to get a more massive thing for me here. And I have somewhere, let's find it here. And I don't know if you guys clicked on it. Find it here. Like this demonstration here, let's actually, if we look at, this is the anode. Okay. So at the anode, what you're actually having, the zinc in this case is acting as the anode. So you have your zinc atoms here. One of the zinc atoms actually loses an electron. As a result, it creates an ion. So what's happening in that anode chamber? Is it becoming more positive, staying neutral, getting more negative? So over here in this chamber here, so if I look over here, it's getting more positive. So if this chamber is getting more positive because electrons are leaving or a negative charge is leaving, what's happening in this chamber over here? It's getting more negative because what's happening is I've got my ion, say my copper plus 2 is jumping on. Actually, let's look at it. So we have our copper ions, and as the electron or electrons come down, they actually go from an ion to a solid. So it actually gets a little more massive. So in an anode, it actually is being sacrificed in some situations. So as this proceeds forward, this is turning from a solid to an ion. This is an ion going to a solid. So whenever we talk about an electrode first and foremost must be a what? Solid, liquid, or gas? What is it? No. The electrode, this thing right here. Solid, yeah. So the electrodes always have to be a solid. Now, we will typically use metallic type electrodes, but you could use carbon, you could use other things that are just as long as it's a solid. So if you're ever asked to identify an electrode, make sure that you actually say that the solid thing and not an ion. Ions are bad. Okay? The next part of this question said, I think you said there's always a negative particle going through the salt bridge. Now, again, this was somebody else that wrote that up. So my English isn't that great, so I wouldn't be able to be correct on that. Now, what's the purpose of a salt bridge?
To keep the neutral charge.
Okay, I like that. So in this chamber over here, if it's getting more positive, we're going to have negative ions flowing toward this chamber here. Because, again, this is getting more positive, so we need to balance that and make sure that it stays the same charge that we started with. Over here, since this is losing those positive charges and becoming neutral, it's getting more what? Negative. So I'm going to have positive ions flowing toward this side. Now, because I can't write on the website here, let's put this guy up. Sorry. So if I say, and let me erase this stuff over here. Actually, let's go to the next page. If I have, say, this is my anode, this is my cathode, and that's my solid, yay. That's my other electrode that's in there, and you get your solution. And then the salt bridge, oh my goodness, I guess. So we have our salt bridge, which is here, and yes, it is very wonderful. So what's going to happen is, if we said that this is a site of oxidation and this is a site of reduction, okay, what we're going to have is, what did I say in the video about anox red cap? How's an easy way to remember that? That the vowels stay together, the consonants stay together, so you have your anode here and your cathode here. Okay. Now, we said that this chamber here becomes more positive or negative? Positive. So to help maintain that charge, we need to have what's called, what kind of ions that flow in that chamber? Are they cathodes or anions? Or cations or anions, sorry. Which one? Anions or cations?
Andrew says anion.
Why? So we need a negative charge. So anions actually are flowing toward the anode. A with A. Okay, so in the salt bridge, your anions are flowing toward the anode because, again, that chamber is becoming more positive as a result of the electrons leaving and going toward the cathode. So what do you think, what type of ions do you think are going here into that chamber? Cations. Yeah, the positively charged ions. And again, cations, cathode. The C's stay together. Okay, so there's a lot of things to help you remember how this thing is actually flowing. Now that kind of looks like garbage as I look at it on the screen. That's not very appealing, so be glad that you're here in person rather than watching the video. Also, when we talk about getting rid of the names here, well, we'll leave that up there. But looking at this, what is the directional flow of negative charges? Do negative charges go like this? In that direction? Yes. And that's the thing. Whenever we have a galvanic cell, we want to keep that circuit, quote unquote, going. So the flow of negative charges moves in a clockwise fashion with this diagram. Now, if I had the cathode on the left side and the anode on the opposite side, then it's a counterclockwise. So, those are beautiful. Mercy. Let's just delete it. Okay. Sorry. All right, so looking at that, so in the clockwise fashion, we have the negative flow. Is there a positive flow going in the opposite direction? The answer is yes. When we talk about current, now if you're an electrical guru, which most of us aren't, but how does an electric wire work? In other words, when you go and turn the light switch on, you hit the light switch, lights come on, right? What's that? Okay, that's too technical. So, let's say that we have our electrons. Okay. And I'll give you another analogy here. Okay, so we've got our electrons. So let's speed that up a little bit. So we've got our electrons. So as soon as I hit the light switch, what happens to these electrons? They start to move. Do they all move at once? No, they actually, one electron moves at a time, and it leaves a space, which allows that electron to jump and occupy that space. Now, in real time, it looks like a river. You're right. But again, just like a river, for this water molecule to move where that one's at, that guy's got to get out of the way. True? Yeah. It's also like if you have a garden hose and you have it, the spigot is turned on, but at the end you have that nozzle. How do you get the water at the end of the hose to the front of the hose? Open up the spigot, or the sprayer, and get the water out so that the water can move forward and occupy the space that water once occupied. This is what we call current. Okay, so as the electron moves forward, it gives an empty space, where here it had what charge right here? Negative. So as it moves out of that space and leaves a void, it temporarily has what charge? No charge, or it's more positive than it was. So the electron occupies that space because it's no longer negative. Here, that electron's not going to occupy that space because there's already an electron there. So again, current is that vacancy. So when we talk about the flow of positive charges, technically on the wire, we don't have particles that flow in that direction, but we have the vacancy that acts as a positive. So we have our clockwise direction of our negative flow, and then the counterclockwise. You can obviously see the counterclockwise flow in the salt bridge, but also along the wire. So again, you've got that flow of positive and negative, and they go in opposite directions. Okay? And those are good questions that could be asked. So it may ask you, show me the flow of the electrons, show me the flow of current. Current is in the opposite direction. And again, I will admit, just like a lot of things that we hear and we say, oh yeah, whenever I turn the light switch on, the current of electrons moves to the light. It's actually moving in the opposite direction. It's moving down the line, back toward where those electrons originate from.
Would they be asking for a conventional current? Or?
No, it would be this. Yeah, that's why I'm saying that whenever I talk to anybody that deals with electricity, current is electrons all moving together. But the chemistry, don't ask me why they had to use the same term, but it's that vacancy. So when one electron moves forward, it leaves that vacancy here. So that current is hopping spaces in the opposite direction. I agree. When I first heard it, I was like, you gotta be kidding.
Wait, so if they ask us which direction the current is?
It's the opposite of the electrons.
That's because of the spaces that it leaves?
Yes.
But if they ask us the flow of electrons?
The flow of electrons is obvious. It goes from the anode to the cathode. Yeah, and normally they'll ask the electron flow. I've seen current a couple times, but it's not like... They'll definitely ask about electrons before they ask about current, which is nice. All right. Oh, wait. No, I want to go back. All right. So let's go back. Okay, so we spent quite a bit of time on that. All right. The second part here. Is it possible for there to be multiple choice questions about asking about the concept of the Nernst equation? I guarantee it. I guarantee it. This was the equation that used to be given back in the day on your equation sheet. They no longer ask us to do calculations with this, but you need to know the concept behind it. In other words, let me explain what this is. So the E cell is the adjusted voltage when you finish, if conditions are not standard. Back here, before I jump to the other ones, this right here, log of Q, what does Q represent again? Products of reactants, and it deals with the same, this is our equilibrium Q. So when we're at standard conditions, what do standard conditions mean again for the solutions? 25 degrees Celsius, and what is it? 1 molar. So we have a 1 molar solution. So let's say that we have, starting off in each of these chambers, we start off with 1 molar solution. So Q is equal to 1 over 1. What does 1 over 1 equal? 1. The log of 1 equals what? 0. So if you do 0 times this whole back end, that gives us 0. So under standard conditions, the adjusted voltage is equal to our standard. Okay. That's the concept. That's one of the concepts. So we don't have to do a calculation. However, get rid of that guy and that guy. Let's say that now we have, say, 0.1 over 1. So the concentration for our products happens to be at 0.1 molarity, and our other one is 1. So this value is less than 1. If you have the log of a value less than 1, so let's write it over here. If my Q, actually log of Q, is less than 1, what kind of sign do you have? Do you have a positive or negative sign for that value? Negative. Good. So you have a negative sign. So if we go back to the equation here, if this is negative, okay, what happens to this part of the equation? It becomes positive. So if your concentration is 0.1 over 1, or that your Q value is less than 1, then your voltage is going to go up. That's the concept. You don't have to do a calculation. You just have to know that if Q is less than 1, it causes that to be a negative value, which causes this portion here to be all positive, which means that we're adding to the standard cell potential, which gives us a larger voltage. If we flip that around, okay, get rid of that. So if we now have 1 over 0.1, now my value is greater than 1, so log of Q is greater than 1, then that gives me a positive sign. Okay, so if I have a positive sign, what does that do to my overall equation here? Makes it more negative, or lowers the voltage. So in that case, if I have this situation, then the voltage will go down. That's the concept. Okay? Yeah.
Does this refer to the galvanic cells?
Yes.
So, in the case of the galvanic cells, you have the two beakers. What would be the products and what would be the reactants?
Aha, very good. Okay. So let's give a hypothetical situation here. Say we start off with a copper electrode and a magnesium electrode. Okay. So those are your two electrodes. Now, the really nice thing is, when you set up the galvanic cell and you place those in the solution, nature will automatically determine who the anode and who the cathode are. However, you're not nature, so you got to say which one's going to be oxidized and which one's going to be reduced. And so based on that information, we want to go to our standard cell potential sheet and find out what those values are, get the most positive value, and then go from there. So based on that, let's say, and I believe the scenario is, that magnesium wants to be oxidized. I know it's like a +2 something. And copper actually wants to be reduced. I think that also gets a positive value. So let's just say that they're positive voltages. Okay, just leave it at that, which gives us a positive voltage. So from here, to answer your question, to determine who Q is, okay, how's Q set up? Good. Products over reactants. What do you mean?
Well, that's my question.
What never goes in the expression? Solids or liquids. Okay. But what can go in there? Gases and aqueous. Good. So is this considered aqueous?
No.
No. This is considered aqueous. So there's our reactant. Whoops. There's our product. So in this case here, Q would be magnesium +2 over our copper +2.
How do you know that copper's on the bottom?
The concentration values. And if they're standard, then it's 1. I'm sorry, say it again.
How do you know which one's on top and which one's on bottom?
Okay. So we never put solids in, so that eliminates those two, right? Then we look at our arrow. So wherever the arrow's at, it's going to tell us who's reactants and who's products. So it's all based on your voltage here. So if it's a positive voltage, that's our most favorable situation. Okay. Now let's pretend that, let's go back. Let's say that, okay, we're not looking at, let's pretend for a minute that that's a 3. Use your imagination. Again, it's not. So that means that now we have to multiply that by 3, and we have to multiply this by 2. Okay. So if I put my copper plus 2 down here, do I care that there's a 2 and a 3 there?
Yes.
Yes, I do. So what would I do to my expression? Put squares and cubes. So in this case here, we would have a total of 6 electrons, so that means I'm going to have 3 magnesiums, so I'm going to cube that, and then I'm going to have 2 coppers, so I square that. Now, I would be very surprised if they asked you to do that with things other than 1, okay, like 0.1, 0.01, things like that, to square and cube. Okay. To find out if this value is greater than 1 or less than 1. I think most of us could figure that out, but they'll generally try to keep it relatively easy. But does that make sense?
Yes.
Okay. Any other questions on that? Here, let's see. So, yes, the concept about Nernst will be asked, but the math will not. So, again, if it's less than 1, that voltage is going up. If the voltage is greater than 1, then the voltage is going to go down. Okay. And then the last one, could you help explain the salt bridge again? Probably the best way, talk about the salt bridge one last time here, is that the reason why the salt bridge is here is to maintain that flow of either negative or positive particles. I can't remember, did I talk about solubility in the chambers? Like, let's see here, we have copper and zinc. Let's say that I put, I don't know, something with a phosphate in here. And so we would form copper phosphate, which is a solid, it's not soluble, or that I'd form zinc phosphate, which also is a solid, it is not soluble. Is that a good thing to do for our salt bridge? No, that is terrible. What we don't want to do is form precipitates in the bottom. What that means is, or in the galvanic cell itself. Because if you form precipitates, you're eliminating these ions that are actively involved from going from a zinc plus 2 to a solid zinc. If you take away those ions that are actively involved in allowing, let's look at the copper. The copper is the one that would be more involved in going from here to here. So if we eliminate those ions to allow it to go from the solution to a solid, you're shutting the whole thing down. So we never want to form a precipitate in either of the chambers. Now, it really wouldn't be so bad over here because this goes from a solid to that, and then we could form a precipitate. But again, rule of thumb, never form a precipitate. So good salt bridges usually have nitrate in it because nitrate doesn't form a precipitate with anything that we care about. And good group 1A metals are another one. So sodium nitrate is generally a really preferred thing. I didn't click on that. So here's how some of those ions, so as the zinc starts to accumulate, I don't really think that the zinc ions are really leaving like it's saying, but if we introduce more negative charges in there, then it'll bounce out. So ignore that zinc leaving because now it's making the chamber more, I don't know why it's doing that, that's bad.
It's like, make it like, because electrons are leaving like that.
Yeah, so
Substances to make it more negative.
So
to counteract the electrons leaving, basically.
But here's the thing, if I have electrons leave and I make zinc ions that are positive, I'm actually adding more positive charges here. If I'm adding more negative charges, why would my zinc leave?
Well, it comes in on the other side. If you put the other side of the salt bridge, that ion goes into the other side.
Right, and on the other side we should have sodium coming out. So the sodium, these are sodium atoms, but I don't know why here they have nitrate going in there. But again, the nitrate is okay. I really don't like any of that. But yeah, that's not mine, so I apologize. But it will help to maintain the charge. So my rule of thumb is nitrate comes in, the zinc ion stays here. Okay, because when I add a positive charge, I want negative charges to come in here and help balance out the charge. If zinc leaves and I got this flow of negative charge coming in, I got a problem. I got a problem because my chamber is going to become more negative.
I have two questions.
Sure.
First of all, would the balance of the aqueous solution change throughout this whole process?
Yes.
So what side would get higher and what side would get lower?
Well, this one, the zinc will eventually get higher because zinc is turning in, solid zinc is turning into zinc ions. This will get lower because copper ions are going to solid copper. But what's crazy is, College Board typically doesn't ask that question. It might give a situation, say, okay, we start off with the 1 molar or the standard solutions, and then we do another scenario where we look at it and it starts off with maybe a 0.5 and a 0.1. But it's really weird. They don't ever discuss how long this goes. I mean, until that gets totally consumed, then the reaction stops. Here's another question. What if I just take the salt bridge and lift it up and out of the 2 chambers? What should happen to the reaction here?
It would stop because one side would get too positive or too negative.
It would stop immediately. So if you lift that salt bridge up, that flow of positive or negative, depending on the respective direction, just shuts it down. It discontinues that current. It's like hitting the light switch. When those electrons are flowing, when the light switch is open, and you shut it off, you've essentially shut off that flow. So it does stop, and it stops immediately. Okay? Yeah, go ahead, I'm sorry.
Why does it start in the first place? Don't each, like if the wire was like cut and like not connected.
Good. Then nothing happens.
Right.
Okay.
Both sides would be neutral, correct?
Yeah.
So then when the wire is connected, why do the electrons move? Like why does that happen in the first place?
It's thermodynamically favorable. It's spontaneous. It's kind of like when you throw a match in gasoline. It wants to burn. It wants to blow up. So this wants to happen because of the voltage. That's the beautiful thing about things that are spontaneous. They want to happen. And if we give them the right conditions, it'll take place. But like sometimes you'll see a switch on here. Like I don't know, I'm being real fancy by doing a switch like this. But if the switch is up, nothing's happening. This can sit in that solution all day long. Nothing's going to happen. And same thing over here. Nothing will happen. But once that switch hits and electrons leave and start to come over here, because the zinc wants to give away its electrons, it wants to do that. And the copper +2 wants to gain those electrons. So that's just what God made and makes it happy. That's nature. Why do we breathe? We want to. All right, let's get to some fun questions. Yeah, Isaiah, I agree. You don't want to breathe. Quit breathing. All right, let's take a look.
I know you're on tape.
Sorry, Isaiah. I didn't mean it.
You don't care.
All right, I think we answered the salt bridge, but a porous disc is the same thing. Now, typically, you might be asked about a porous disc, but it acts the same way as a salt bridge, except it looks a little funkier. I'll admit, I'm not an artist here. Yeah, well, it's a lot more expensive, yeah. Did I say that in the video? Yeah, so I don't get to handle expensive things. So all the porous disc allows to happen is that as this chamber becomes, we'll say, becomes more negative, then that means that negative ions are simply going to flow away from that. Or if this one becomes more positive, then positive ions flow away. Or we can counteract if this one gets too, well, it automatically does that. So yeah, so the positive can leave and just to balance it out. But everything else, the wire is still the same, and your electrodes, etc. Okay, so it's not as romantic because now it takes out possibilities of having precipitates form, which is a major question they like to ask.
Why can't the electrons go through the aqueous solution? Can they not do that?
We'll talk about that later. They will in a different scenario.
Right.
Yeah.
And then if the two sides balance out, then like if you had it connected by a salt bridge, you have to add in these other compounds.
The ions and cations.
Right.
Yeah.
But in here, you don't have any ions.
In other words, they go through that porous disc. So it has a big enough opening to allow the ions to pass through.
All right, but not like
rush through.
electrons.
No, electrons won't go through the water yet, or the solution yet.
Right. Okay.
Yet. That's coming up, and trust me, you don't want it to come up. Yeah, that's exactly right. You're not going to be happy. All right. What is a cathode? What is a cathode?
It's the side that is reduced.
Positive.
Okay. First and foremost, it's an electrode. Okay. So it is a solid thing. Okay. So we even sometimes will refer to the chamber as being considered the cathode, but really it's the electrode. It is a solid thing. Okay. So it's the chamber where what takes place? Oxidation or reduction? Reduction. Remember, keep the vowels together and the consonants together. So I had on the video an ox, red cat. Okay, so at the cathode, reduction takes place, or the reducing reaction takes place. And what happens to the mass of the cathode as this goes forward? It'll increase. Very good. Okay. Awesome. Anode.
The opposite. It's going to get reduced and the mass is going to
It will be opposite.
You mean the mass will get lower. Please don't use the word reduced around an anode.
sorry.
So it is a side of oxide. It is a solid. And notice that I'm not saying it's a metal. We will typically have it as a metal, but it has to be a solid. And it is where oxidation takes place. As it proceeds forward, the mass decreases. Will the cathode or anode ever show up in Q? No. That's a no-no for these guys. Okay. Only the solutions. Oxidation half reaction, that's where the electrons are produced. The reduction half reaction is where the electrons are captured, quote unquote. Okay. Any questions on those terms? Looking at number 3, why isn't the value of the cell potential multiplied by the same integer used to multiply the half reaction and balancing the equation? What I really believe this question is saying is, why don't we multiply the voltages? Okay, so if you have a coefficient of 3 and a coefficient of 2, so it gives us 6 electrons total, why don't we multiply the voltages? Yeah. It's an intensive property. Very good. So as long as you have it, you'll have that voltage. Now, the other component is that changes it is the concentrations of our solutions. So the Q, but our voltage, notice that remains fixed. As long as you have it, you have that voltage. But the concentrations of your aqueous will actually depend or actually alter the cell. All right, I went ahead and drew up the pretty little galvanic cell. So it's beautiful. So I put the anode on the left side, cathode on the right side, and I had some people ask in first hour, they go, is the anode always on the left side? No, I think I do it because I'm like alphabetical, but sometimes they'll just give you like a galvanic setup, and it's up to you to make sure that you put the correct electrodes in the correct spot and then designate whether it's an anode or cathode. I don't care if you start with the cathode on the left side and the anode on the right, but if it's specific and says, okay, in this chamber we'll have reduction taking place, make sure that you design it accordingly. Okay. So again, whenever you're identifying the electrode, make sure that you're putting the solid. It will not have a charge on here. It is not magnesium plus 2. No. Bad. Okay? And they are solids, so solids do not have a charge. Now, in the solution, you have magnesium plus 2, but generally we don't ask about that. I mean, maybe it will this year. Who knows? Okay? And keep in mind that in the salt bridge, anions, the negatively charged particles, move toward the anode. The cations, the positively charged particles, move toward the cathode. The flow of electrons for this diagram goes from the anode to the cathode. And notice that I said from anode to cathode. It goes from the metal to the other metal. Okay. And then I also put the scenario on here. I wanted to know what is the charge. So there's our voltage. And that is for the E cell potential. Okay. And if it's under standard conditions, then the E cell is equal to the E cell potential. Okay. Any questions on that? Getting a lot of information. Isaiah's learning a lot. Isaiah, be careful. All right, looking at number 5. So it wants you to answer the following questions using the data from the standard reduction potential 25. Now again, back in the day, you had all those values. Now you get a table, so it's a little easier to work this out. But the question's asking, is hydrogen plus 1 capable of oxidizing copper to copper plus 2? So I went ahead and wrote the half reactions. And here we have, that's the oxidation value, or the oxidation potential, which is the opposite for the reduction potential, and it gives a negative 0.34 voltage. Also, be sure that when you're looking at the reduction potential values or things, make sure that you're not making something up. It has to be the same way that's on the sheet. All right, so you can't just say, well, I went from H plus to, I don't know, H neutral all by itself. So this is actually on the equation sheet as written, and it does have no voltage as a result. So in this case here, if we did the math, will it or will it not?
Wait,
No.
it's not going to spontaneously do it.
That's all the question's asking at this point.
It doesn't say spontaneous.
Okay, that's good.
So is there a way that you can manipulate the situation so that it doesn't have to be spontaneous, but it'll do it anyway?
Okay, until we talk about the non-spontaneous situation, everything that we're dealing with right now deals with spontaneous.
Sure.
Okay. But yes, I could get this to go. But on its own, without me doing anything, it will not go.
The question's misleading.
Oh, it's very misleading. It's assuming that we're still in galvanic, that you don't know about electrolysis yet. Don't think about electrolysis. Forget you heard that word. That's good. Yeah, I'll be.
What does that mean,
I'll hope that you learn that word sometime soon. All right. Since we got a few minutes, let's skip ahead here. And I started to work on this one first hour, but we ran out of time. So here's a situation. It says in a galvanic cell, you have the concentration of lead plus 2 goes from 1 molar to 0.25. Concentration of magnesium goes from magnesium plus 2 is changed from 1 to 0.1, and temperature 0. First predict the oxidizing agent, reducing agent for the spontaneous reaction in the cell. Okay, so I started to write the magnesium was being oxidized. So there's your spontaneous. Is that misleading? Do I want to flip it?
Oh, no. Is that what it says on the sheet?
I don't know.
Sure.
So we will have a positive voltage. Okay. All right. And so first it wanted us to do that. So who is the oxidizing agent? Let's start with that. Who is the oxidizing agent? The lead plus 2. Okay. Remember, the agents must always be on the reactant side. Okay. Things that are oxidized, things that are reduced must always be on the reactant side. Some of you missed that on the quiz. Who is the reducing agent? There you go. So Mg plus 2 is the reducing agent. Okay. Now, is it possible for agents to have no charge? Yeah. Yeah, it's very... Actually... Ooh, I messed that up. That should be plus 2. And that should be no charge. My bad. Yeah. My bad. Yeah, that makes sense. You're right. And then calculate the cell potential for the standard conditions. And it says use the Nernst equation. So here you go. You've got, what is that value there? 2.24. Okay. So we got 2.24. And that's our value there. So if the conditions are here, negative 0.0592, hold on. How many electrons are being changed? 2, good. But the log of 1, so your voltage is 2.24 volt, right? Because what is the log of 1, Isaiah? 0, very good. And then, that last one, under the new condition. So, let me ask you this. Let's do the Q before the bell rings. So, what will the Q look like? Products of reactants.
0.1
So,
over 0.25.
so magnesium plus 2 over lead plus 2. So magnesium is that over 0.1. So is that less than or greater than 1? Less than 1. So the voltage will go up. So when you do your calculation, it should get higher.
Hey, why can't I see myself on this?
Nobody wants to see you, Luke.
He's taping the screen, there's no camera, idiot.
Have a great day, guys.